Hello, good afternoon, good morning from where you are. I'm Nabih Cherradi from Desert Technology and SOLARUNITED, and I will be the moderator of the sixth session of today. The session is photovoltaic specialties. I would say specialties in terms of technology applied to different market segments. Is going to mainly address also some, in certain manner, the niche markets by certain products. We have four presenters today from prestigious institutes and companies, and each of them is going to give us his, I would say, development in the technology and the application of the different technologies on the field they are working on. Of course, when we talk about the specialties on the PV, we always think something which is fancy, which is, I would say, not common. However, today, even the specialties, they are taking more and more parts of the market segments, I would say. The best testimony of that is the extremely rapid development of the floating photovoltaic, which now overpass several gigawatt installation. And it's still at its start because it's very interesting as a technology, especially where the land is very problematic. And the best example of that's what's happening and what's going on in Singapore, for instance. The other applications are, for instance, for that, I would say what I can call it, the niche markets, even also if it's not really a niche market, because the building integrated photovoltaic, which is always, I would say, at its starting block. Some projects have been developed, and this is, of course, I'm not talking about the rooftop. Of course, the rooftop, it's something which is special, even if they are integrated. It's hard to say that it's integrated installation, but really the building integrated photovoltaic, what I can see and I can think about, it is really in the facade, in shade, and all these things. And unfortunately for that market segment, we should, and the industry should think, and we're gonna hear Jean-Luc from AKUO regarding that, and probably he will give us his point of view. If not, we'll ask him about the integration of the architect in the scheme, because if the architects are more and more aware about the benefits in terms of power, in terms of the design that they can get out of from the BIPV, I would say that more projects will be, especially the prices are going more and more down. And in the contrary, with the normal installation for the BIPV, we call it, the cost is mainly with the, I would say, linear meter. It's like for windows. So it's something which is windows facade, and the prices are different, and a different way. So I think that there are a lot and more to come in terms of applications. Among these, what we'll be talking today is that the BIPV, the VIPV also for the vehicles is something which is very interesting more and more, and just session before shows a lot of developments ongoing, but it's still, of course, at its really early stage for, I would say, mass applications. However, for the BIPV and the floating, it's going on very well. So without delay, because I would like to give more time to our presenter for their presentation, like that we can have as much as possible of questions. So please, this is addressed to the audience. If you have any question, whether it concerns the session or the coming session, whatever, please, you have ask your question in the Q&A in the chat, and then I will report the questions to the presenter. So without delay, I would like to give the floor to our first presenter, which is Eszter Voroshazi. Sorry, pronunciation, from IMEC. She's gonna give us a presentation entitled EMEC'S Technologies and the Roadmap for the Integrated PV. So Eszter, the floor is yours.
Thank you very much. Thank you for the introduction and welcome all from around the globe. So I have the honor to start the presentations. Let me share my screen. So thank you again for the invitation, and let me just first start with introducing myself, as you might not know me all. I'm Eszter Voroshazi. I'm leading the PV activities at IMEC. And today, what I would like to share with you is our vision, technologies we develop for integrated PV. IMEC is a Belgian research center founded in Leuven, but now, as you will see, operates in many different sites. IMEC focuses on nanotechnology, digital and energy technologies. And our mission is always to explore and validate and upscale technologies ahead of industrial needs. IMEC is also a partner in Energyville, jointly with Vito University of Hasselt and KU Leuven. The partners in Energyville are aiming to accelerate the energy transitions through a research really integrates the technology research, solar storage, power conversion tools into building districts, networks, and really scale it up to look at market and strategy level. So I think integrated PV, as you understand it in this setting, is really one of the heart of the matters that we are looking at. And just to tell you something interesting, we've recently built a new campus. We are located in Genk, very symbolically actually at the site of a former coal mining site. But so let's move into the PV part. At IMEC, our activities are more and more focusing on integrated PV technologies. This is really motivated by a major market and societal pull to make PV as the main pillar of the future energy system. And to make this happen in densely populated Europe, integration will be key to our view. What we use is our more than 30-year-long history and background in PV innovation. And what we also add to this more and more our system knowledge. Because as I will mention that, I see that this will be really critical in integrated PV. How we are doing this innovation, this is something that as an institute, we cannot do it alone. So we really tap into our material technology and application partners. When looking at integrated PV, I think you probably share my view that having the acceptance of integrated PV by the public, by the different sectors, aesthetics is more and more in demand, seamless fit to fit the size, shapes, but all needs to come at affordable costs. As in the introduction we mentioned, originally integrated PV has been something unique, something very prestigious. But in these pictures already, I aim to pick photos of where it becomes more and more cars, buildings that we see in our everyday life for everyday people. But when we look at these different applications, I also see an important challenge coming up, hearing from all the different companies that it's very nice integrated PV, but all these different applications have very specific requirements, not just in terms of fitting into the form, but also in terms of safety standards, regulations, standardizations. So how can a BIPV developer deal with this? Is it mission impossible, you would wonder? Well, to our view, still a few ingredients, if you would take just a few humble ingredients, but combine them smartly, we believe that most of the wishes and requirements in aesthetics customization could be answered. Variety management, so really adopting a new way of managing both your design, production will be key here. Examples for this, we can look at, for example, the automotive sector, where when you order your new car or you select a new furniture, custom furniture online, you can more and more play with different buttons to design your own, you have the feeling, though still it's a smart combination of a few ingredients. So what are these what are these ingredients for integrated PV? Well, one of the key parts that I like to really emphasize and start with, that more and more, especially as PV specialists, we need to understand that the application and not the PV-centric design is key here. So the PV should fit the form and the functions that is dictated by the application. They define the boundary conditions, and PV, just from technology side, cannot make its push off anymore. The other element which will be key, and we've heard this many times, that aesthetics and seamless integrations are a must. And here in my talk, in the rest of the talk, I will also talk about coloring solutions, but also something that's often forgotten, that next to coloring, one very critical element is to make sure that the PV, especially the most visible part of PV modules, often disliked by architects or other product designers, the metallization needs to become invisible. So I will talk about what are our solutions that we see that will be critical to solve this challenge. Next to this, getting the current out, junction boxes optimizers need to electronics that can deal with the regular shading or dynamically varying shading will be an equally important part on technology innovation level. But this will deal about the aesthetic part, but there is also the customization part, where everybody wants custom, but still at affordable cost. So there we really see that mass customization approaches, tools, technologies to fit automated module assembly and custom sizes will be critical. And this is an element where it still needs a strong attention jointly from industry research centers to develop this. In the mass customization, in our view, what we see that standard or nearly finished so-called blue cells that can be cut to size will become an essential building block to build custom modules. This will allow to bring on a more cost-effective solutions. And last but not least, I will also touch very briefly on that sustainability materials and technologies will be key. And in integrated PV, we have actually the chance that we are still designing new type of modules, new type of processes and products. So we can really from the start integrate the sustainability aspects. Next to this, we've talked a lot about BIPV, and I personally see it also BIPV in the integrated PV field as one of the trailblazer applications. It really kicked off the integrated PV sector a few years back. We very recently did the comprehensive survey in the EU BIPV market. And what we've seen that today already more than 120 companies are active in the sector. And these companies actually offer more than 130 products. And looking at the different products offered by these companies, we find it very interesting that there is an equal share of facade roof products. And then generally in the portfolio of even just smaller companies, there is actually a wide variety of products already. And looking at the product distribution that you see on the slide, you clearly see that there is not, one cannot say that there is just one or two dominating BIPV element or product. So it already shows that already at the start of BIPV that we are experiencing now, there is already a need and a demand for variety. And what we see in the future coming up is actually that in a 5-year time, this will further increase, definitely. There will be, we really see that the product portfolio and variety will just keep on increasing in BIPV. We also strongly believe that VIPV will become as a common option to add in your car in mid and high-end cars in just 5-year time. So we will there experience a very fast development and deployment. And next to the custom elements, off-the-shelf integrated PV elements will become available from building companies, from OEM, from grass producers. So there, the two will very happily actually, to our view, coexist both custom and the more semi-standardized elements. But for all of them, the few technology blocks I like to show will be, believe, key. So let me now in the second part of my talk move into more on innovation aspects that we've been also working on or jointly with our partners. So one of the elements, aesthetics, is, as I call it, it's really the door opener. It's very difficult to talk to product designer before you have anything that looks just a bit aesthetic. There one really have actually two very big categories to look at, and many solutions actually exist. Transparency, from all black to fully transparent through semi-transparent. There's a lot of different variety available, and I think will be really needed to make sure that integration can happen in a variety of products. Next to this, I think what is really remarkably progressed in the last period is the color and pattern that's available through PV modules. So here on these pictures that you see, well, these are PV modules. You probably think that it's just kind of a Belgian joke, but well, these are actually well functional and generally reasonably performing PV modules. We're using colored interlayers or colored front glass. One can achieve nearly full integration into the environment. So for me, these elements and actually generating more and more variety, keeping on generating variety will be key to match all the demands that the building sector, the car industry would have. When we are talking about colors and aesthetic, what's often forgotten, especially when we look at these coloring options here, that invisible interconnection is one of the key elements. Because all of these layers that you can see, they are actually still, you can see they are see-through elements. So having a neutral background behind the colored layers is really critical. So there one really needs to work on and make a choice for a nearly invisible cell and interconnection technologies, as I call them. There are actually variety also available there. So companies can choose or have multiple technologies in their portfolio. Currently, one that's quite commonly used is actually taking still regularly made cells using regular tub and stringing process with metallic bus bars, but trying to paint or somehow color the bus bars black is one of the solutions used by certain companies in the field. Although it has its limitation technical challenges, and definitely it will not scale or not increase, it actually reduces performance. So it will be, to our belief, something that will not exist long term. What we believe that multi-wire and shingled cell interconnections will become probably the mainstream. This has been also our focus in the last years in development. These technologies still have some metallization on the front, but they are below 200-300 micrometer width, which actually from a distance becomes nearly invisible to the eye. Next to this, of course, one needs to also mention back contact cells, which very elegantly solve the challenge of putting all interconnections on the rear side of the solar cell. There are one or two players who offer devices and technologies with these cells, although for the moment it's still a smaller market segment. As I mentioned, at IMEC we have been focusing actually mostly on multi-wire interconnection technologies. You might have already heard that we have been developing actually at IMEC ourselves, proposing a technology which relies on busbarless cells and using a woven foil to interconnect busbarless cells. So it's a variant compared to the smart wire technology, but with certain differences. And let me explain this. To interconnect the neighboring cells in series connections, we use actually a woven fabric. You can really imagine a textile, but instead of using cotton as filaments, we actually use encapsulants and solder-coated metal wires for the interconnection. With this, we create a fabric, and these woven sheets can actually serve multiple purposes. They can be served to laminate as a lamination material, and at the same time as interconnection. So we really combine the two layers of a module into one layer. But we also aim to combine two process steps, the soldering and the lamination processes, in one process step. These technologies have been for the moment entirely developed at IMEC with partners. And next to the combination and the aesthetic arguments, what we also really see is one of the key advantages of this technology for building integrated application is that through a smart way, actually we can remove the edge ribbons and create custom patterns in the module. So at the edge of the module, we don't need any more ribbons that are often needed to be positioned manually in BIPV manufacturing. But this actually can be smartly done by using a woven fabric rotated 90 degrees. For this, we also adapt the cell metallization. But all these adaptations can be implemented and can be made, how to say, variety proof, so adapt to a large variety of different modules. So to demonstrate this concept, let me show you also now in real photos and videos an assembly, not just a SketchUp. So what we are doing here is that you see on a glass panel, you see our woven fabric, where we position a bus parallel cell, then another foil, another cell. Then you will see that we rotate the woven fabric 90 degrees to make the connection between neighboring strings in a PV module. And this way, we can actually create the module. So this way, actually, using these fabrics, which can be made in different sizes, lengths, shapes, we can really adapt to a variety of module layouts just with these foils as building blocks and standard cells. We can remove the end ribbons, which are often actually elements that need to be hidden in integrated PV applications. To make this at automated and custom automation level, we have been working with a partner, IPTA, to actually create a tool which can do this that you will see here. Let me just start this off. So here comes the difficult challenge of having a video running. So here you see the example of what we've designed. Here you see it actually a bit slowed down, where we can give into a computer whatever module design we like. So we here given the challenge, okay, let's please make the same module you've seen on the left side. And then picking up cells, woven fabrics, the module can assemble your module in the custom size and shape you asked for. So this is, for example, one of the view examples we see as an option for custom manufacturing of PV modules. So going further, jointly with partners, we implemented this technology in products, existing products where the architects or the building company were asking for a next generation, something that is more aesthetic, more cost effective, and at the same time have higher performance. And by the way, they also said we like to reduce cost. So at the beginning, we thought, well, this sounds an impossible challenge, but working with the interconnection technology, we could achieve these goals. So let me show you one of the first examples was a solar roof tile jointly with Eternit. Their product is called Solasia, where you see also at the bottom of the slide a layout of the module. And one of the big challenges for this product has been actually laying at the edge of the PV module. Oh, my apologies. You probably don't like to see this. One of the challenges has been that how to actually deal with the edge of the PV module. Having three strings of cells, they actually had to make a quite unfortunate connection of bringing a full ribbon up along the side of the module. So here with our multi-wire interconnection technologies, what we've actually offered them to remove this cumbersome edge connection, which was leading to a lot of extra cost, performance loss, not to mention poor aesthetics, is actually that we completely redesigned their modules with our interconnection technology. Here you see the comparison, where without any front glass treatment, just using multi-wire interconnection technology, as you see, we could create a very homogeneous look. But we've also redesigned for them the module layout, where we created them actually different options. And with a smart way of doing the layout, we actually could bring together, fully remove the need of lengthy edge ribbons. So this has been one of the examples where we've seen that smart combination of ingredients can lead to a variety of an interesting alternative. With the same technology, so still using the same ingredients, we have been also working with a glass company making BIPV demonstrators with various cell spacing. Also making PV laminates with a specific glass coating, which if you look under a very specific angle, you could still see the cells and the interconnection. But actually, as soon as you turn it to the angle that an everyday person would see in front of the building, actually you only see a reflective mirror surface. I have to apologize, you see a bit the mess that in our research lab here, but you see that actually it's a real life module, it's not a mock-up. We're using also the same interconnection concept we started to develop also for back contact cells. As you've seen in my slides, every time we have been developing these technologies jointly with a building company and also with the BIPV module manufacturers, because we truly believe that these designs really had to come actually from the building company. Requests, demands, requirements cannot be set by a PV specialist. They need to come from the end user. On this journey to develop this technology and demonstrators, what we've also seen that just developing an interconnection technology might not be enough. So that's why we have been really also looking how to create an ecosystem always around our innovations. And let me show you actually the ecosystem and the partners behind this woven interconnection technology in this video. Can you hear the sound now?
Als je in Vlaanderen rondkijkt, dan zie je dat zonnepanelen echt wel een succes geworden zijn. Nu komen we langzamerhand op het probleem dat we in Vlaanderen eigenlijk niet echt veel plaats hebben. En dus gaan we naar oplossingen zoeken om met de beperkte plaats die we toch hebben, zoveel mogelijk zonnepanelen te kunnen plaatsen. En daarom dat we in dit project gaan kijken naar BIPV-panelen, Building Integrated Photovoltaics. Dus we gaan proberen van zonnepanelen te integreren in bestaande bouwelementen, zodat we alle gebouwen, structuren, bruggen, noem het maar, kunnen actief zonne-energie laten produceren. We hebben in dit project gewerkt om panelen te ontwikkelen die flexibel geproduceerd kunnen worden, die mooier zijn en die de efficiëntie behouden van de standaard zonnepanelen.
So to make solar cells aesthetic, one of the critical things is to make the metallization look nearly invisible. That's why we especially focus on the cell interconnection in our project. Today already, solar cells are made more efficient by creating more and more solar cell lines on the front. But what we do is instead of just making more and more lines, we actually make a large amount of small metal wires. And our innovation comes from the fact that we integrate these fine metal wires with the encapsulant. We create a flexible fabric which interweaves the conducting and insulating wires together in one layer. To realize this innovation, we needed to tap into a variety of expertise: solar energy, chemistry, industrial automation, and of course, weaving.
Vlaanderen heeft een heel lange traditie in textiel. VDS Weaving is een derde generatie familiebedrijf en wij focussen vooral op technische weefsels. Dus voor ons was dit IMEC-Icon-project met onze VDS Weaving expertise een heel mooie uitdaging om bij te dragen aan de toekomst van de duurzame energie. De ontwikkeling van de juiste snijmethodes was heel uitdagend omdat er heel sterke restricties waren, vooral naar de eigenschappen toe van het encapsulant en ook om de rechtlijnigheid van het weefsel te kunnen behouden in het finale product. En wij zijn heel tevreden dat we daarin geslaagd zijn.
To make BIPV modules happen, in flexible sizes, shapes, forms to adapt to the building, we needed to automate the process of assembling the woven foil and the solar cells. This was a very difficult challenge, especially to handle the very flexible and thin woven fabric and position it with millimeter precision. We made this a success thanks to the new tool and process developed by our partner IPTA.
op dit moment hebben bewezen dat we met onze interconnectietechnologie efficiënte panelen kunnen maken. De volgende stap is nu dat we dat moeten doen op grotere schaal, dat we dat kunnen moeten automatiseren en dat we moeten de kosten natuurlijk naar beneden krijgen. En op die manier zullen we zonnepanelen kunnen maken die ons een duurzame toekomst kunnen verzekeren.
So with this, I also wanted to emphasize that beyond technology, one can really also create an ecosystem of industrial partners, sometimes at partners that we would not think at first hand in Europe for the integrated PV. So just as a concluding word, as I mentioned, I think integrated PV can be answered with few ingredients combined smartly. We can match the aesthetic and the customization requirements. BIPV, as I mentioned, I really see it as one of the first applications that open the door for a variety of integrated BIPV sectors. Aesthetics is really crucial. There, multiple coloring solutions are ready and available. Advanced, nearly invisible interconnection technology is a must. These technologies can really help to make modules more aesthetic, but also are critical and need to be thought that they are made automation ready, but yet they can also fit the flexibility of module layout and module production. What we also believe, in view of time, I haven't talked about this, but tandems will become really the next generation workforce for meeting the high watt peak per square meter demands of integrated PV. We envisage at IMEC that actually some of the applications as VIPV will be the first adopters of tandem silicon perovskite devices that will appear very rapidly. And last but not least, I also like to call for everyone working on integrated PV to keep in mind recycling sustainability. Ease of recycling by using similar materials as standard PV panels will not only help the cost, but it will be also crucial to make these BIPV elements more easily recycled in standard recycling facilities. With this, I would like to thank you for your attention, and I'm very glad to answer your questions.
Okay, thank you so much, Eszter, for the nice presentation you gave us. It was very instructive. It was including a large, I would say, applications, technologies, and I would say the hope for the future deployment of the BIPV.
There is definitely hope. There is hope.
Yeah, and as you said, that's one of the most, I would say, natural application of the photovoltaic is the building at first. And I think that we have to think how to include the architect. In my experience, what I noticed at each discussion with the architect regarding the integration of the solar panels, they were either, I would say, very reluctant because of many considerations. As you know, that's the certification for the buildings are completely different than the normal certification of the modules, because it becomes, I would say, a part of the construction material. So this is one of the problems that's rise up. But I know by experience also in France that there is one certification which is working very well, and I even had some discussion with some architects regarding that certification, which is quite enough. But I don't know, frankly speaking, what's going on in the other countries. So the certification of the modules as a part of the construction is one of the issue that's always raised up. The second one, and the most, I would say, critical one, is the cost. And all the people, they are, how much is gonna cost? It's gonna increase the price of the building. And as you know, in the real estate, we always look cheap, while the real estate is going up, which is completely incredible. However, and what also I saw and what you showed to us in your first picture, which is how we can benefit, for instance, for the renovations. And I saw a lot of benefits in the renovation, and especially the biggest benefits beside the fact generating the power and all these things is that the building will have its value increased. It will give a lot of added value to the existing building. So this is also a very interesting applications. The point that I really liked, and also it goes exactly on what happened with the electrical cars 20 years ago when the first, I would say, program was launched, is regarding they made some survey, and it shows that 90% of the drivers drive less than 100 kilometers. And in that time, having a car of 150 kilometers was more than enough. And the experience was very, very successful, but due to different lobbies, the project was killed. And the idea also of applying the photovoltaic and small cars for city applications or something like that for short distances, it's also a very interesting idea. But I think that is going to need also time. The last point that I also noticed is you spoke a lot about the aesthetic, and even the aesthetic is one of the questions that comes from the audience, that the question was, I think that the biggest problem for the BIPV is the aesthetic. We are facing these challenges now. So I don't know what you can answer and how you can answer in spite of what you presented in your...
Firstly, I would like to acknowledge the question and the audience in the sense that aesthetics, I think, will be key. The interactions we had with architects, many of them told us, well, as long as it's not aesthetic, we cannot even talk about cost. So what we need to understand, and that's, I think, really needs to come from the architects to define what they find aesthetic. And then we as PV technology community should follow and make it happen. Though I encourage really the audience to explore and what happened, because in the last 1 or 2 years, major progress has been made in aesthetics. So there, as I started, yes, there is hope. There is actually major technology progress there. So a lot of coloring solutions are entering the market, passing certification. So there is definitely there a major progress. What I think you mentioned something very interesting that I wanted to raise, and maybe will become a bit of a question and discussion point, the certification part, that indeed that can be a major hurdle. And we realize that current IC certifications of modules are actually not meeting the need of integrated PV, which has all different sizes, shapes, and colors. You, strictly speaking, don't have your IC certification as soon as you change something. So I think that's a very interesting point that would be raised rapidly and solved as community.
Okay, so yes, absolutely, the certification is one of the issue afterwards. The other question that comes also from different audience regarding the module color.
Yes.
And the module colors, what I know, that we lose a lot of efficiency and power. And this, if versus the cost, it will increase. This is one point. The second point, what about the durability of that colored front glass? Mm-hmm. It's a kind of, I would say, painting somehow, and through the time with the erosion, what is going to happen?
Yes, absolutely. One needs to, indeed, as we said, aesthetic is important. It's important in year 1, and it needs to say the same in year 20 in a building. So to answer first on the aesthetic question, all the coloring solutions that exist, most of them are actually inside the module. So there is the first protective glass layer, and the interlayer or the glass coating is inside the module, inside the package. So it's protected from the environmental element. They are all very strictly under scrutiny of the various reliability testing. So the solutions that come on the market and become available, they are passing the strict reliability standards and also aesthetic standards in the sense of verifying that there is no color change.
Okay.
So I think there is definitely there the progress that can meet the demand.
Okay. Okay.
And then there was your question about performance loss versus cost, how we deal with this. The color will lead to performance loss. It's unavoidable. It's just fundamental physics. Though very smart solutions, as you've seen it also in the video, there, in some cases, the video zooms in, you see that smart coloring solutions actually allow to reduce the performance loss only to 20–30% compared to the, how to say, non-aesthetic, non-colored version of the module.
Okay. Okay. So I would like to thank you very much, Eszter, for the nice presentation. That's
my
really
pleasure.
Covered a lot of topics regarding the aesthetic, the cost, and all the applications. Before we go to the other speaker, I would like just to answer directly Mr. Durga Prasad, because he's asking about use of the microphone for the question. No, please, to the audience, just write down in the chat your question, and then I will ask them to the presenter. Please, thank you so much. Having said that, so we move now to our second speaker of the session, is Mr. Martin Heinrich from Fraunhofer Institute, and his presentation is Integrated Photovoltaic Potential and Technologies. So Martin, the floor is yours, please. Thank you.
Yes, hello, thank you for the kind introduction. And so I'm Martin Heinrich from the Fraunhofer Institute for Solar Energy Systems, and I'm concerned with the integrated photovoltaics and leading a team for integrated photovoltaics concerning the module technology of integrated photovoltaics. And today we have heard from Nabih that integrated photovoltaics has always been on the edge to be a niche market, but we should actually be more proud of ourselves in the integrated photovoltaics market, and we should not be more. We should be more than a niche market in the future. And I would like to lay out a little bit of a vision as well here with my presentation. First of all, we have the ground costs, which are shared by other structures which are already required. So here we could argue that the ground costs are not required for calculating the LCOE of a PV system. The second, I would like to mention that we can actually partially reduce the cost for mounting and wirings, because we can actually already use structures which are available. Thirdly, I would also like to argue that integrated photovoltaics also benefits from the same trends as for utility scale photovoltaics. So modules are getting cheaper, as well as also inverter costs are getting cheaper. So here we benefit from the same trends, especially for solar cells. Here we have benefited a lot from the utility scale market. And there are, of course, some additional options or additional features for integrated photovoltaics. Integrated photovoltaics may, in certain cases, replace other materials. For example, facade materials in the building integrated photovoltaic sector. Additionally, we have some other customer benefits which are made available with integrated photovoltaics. For example, some shading of areas. So these are one of the main options, and where we see where integrated photovoltaics makes sense, really reducing the cost. But there are also other options. Integrated photovoltaics may open up new markets besides government-driven markets. Yeah, they can be free from subsidies, so any government plans available. And here on the right side, I would actually have a quick example of such a technology. This is the Solar Gaps. It's Solar Blind offered by them, and they actually integrated the solar cells here in the blind part. And it's an automated plant, so it goes up when the sun is not shining, leaving the sun on, and when the sun is shining, it goes down and generates electricity. And they actually not only made this solar blind as a solar option, but they also manufactured the inverter and the motor of the solar blind. They had a planning tool, and they even have an app where you can actually see how much electricity you generate, or even how much money you save when using those solar blinds. So here's a really requirement, a new module technology, and the module manufacturer actually is not only module manufacturers only, but also whole system designer or system provider. So here we have new markets opening up, which are not featured or covered by the utility scale market. And of course, we have an opportunity for local production. We have high customization, which is necessary for those for this technology, and for high customization, you always need a individual planning, which is a good opportunity for local production. And of course, you need to know the local market quite well for this technology. So after this short introduction, why we should bother with integrated photovoltaics, I want to actually introduce all these abbreviations used within integrated photovoltaics, and then talk a little bit about the technologies for integrated photovoltaic. So for integrated photovoltaic, I actually don't want to tell any definition or anything. I want to explore the different options, which we also develop at Fraunhofer ESA. So first of all, we have agrivoltaics. Agrivoltaics is basically putting solar modules onto agriculture areas, agriculture land, and here we can really avoid the land usage conflict, where you have to decide if you want to use the land for agriculture or actually for photovoltaic solar power generation. Here the main focus is really on the agriculture area, and the secondary is actually the PV energy generation. And this opens up a new opportunities. For example, the crops or the shading can be adjusted such that the crops actually may provide higher yields in areas where there are previously not such high yields affordable. So this opens up really new opportunities. Disadvantages are, of course, you have a higher structure required, yeah, so that harvesting machines and tools can go below this structure. So there's an added complexity for the racks and mounting. Usually you have a larger distance to the grid connection point, and an adjustment of the legal framework is actually necessary for this option to really work, because currently agriculture areas, they are not prone to be or defined to be able to generate electricity. The next option are floating photovoltaics, which I would like to introduce. Floating photovoltaics is basically covering water areas. For example, here on the right, we see a gravel pit mine where photovoltaics modules are installed, or water reservoirs, or in Germany, we have a lot of brown coal open pit mines, which are flooded after usage, so they can also be covered with photovoltaic power plants. Here we have potentials that the generation potential is actually higher because of a cooling effect from the water below. Also, the shading of the solar modules decreases the water temperature, and it reduces the evaporation of the water, and therefore water loss in reservoirs. Disadvantages are, of course, also an added complexity for the mounting and servicing of the PV panels, and also water protection requires specific materials to be used in these locations. Also, the legal framework may have to be adjusted in this case. A third option I would like to introduce are urban photovoltaics. Urban photovoltaics is covering city areas, parking areas with photovoltaic modules. And here in the pictures are a few examples from designers. The main goal is the protection for excessive heat of larger sealed areas, and providing shading, lights, or even charging points at these locations. Usually you have an easy connection to the grid point, and you may improve otherwise very sterile areas with some nice visual designs. Disadvantages are, of course, you need to discuss really an overarching concept, because not only the functionality is necessary, but also the design is really necessary. And of course, you have a higher planning effort because of the individual design of the devices. Then as a next option, we have road integrated photovoltaics. Here, I'm not only talking about integrating the solar panels into the roads itself, but also on, for example, noise barriers or the roadside areas. Here in this case, there's really no additional land usage required. You can actually use land which is already used up by humanity. You also have a reduction of the mounting effort if you compare that to installing both systems separately. And you also have often a shorter distance to feed-in connection points. This technology, since you have a lot of large areas available, has also the potential for new standard module technology, new standard module design. Disadvantages are increased requirements for the module design, especially regarding safety. Next, I want to talk about building integrated photovoltaics. Of course, we have the advantages of CO2 reduction, net zero energy buildings or plus energy buildings. Of course, we are very familiar with. It can also be a cheap energy source in remote areas where there's no grid connection available. And of course, you have low additional installation costs for facade or for the rooftop. Disadvantages are that the module is really a construction product, so there's no standardization possible. It also requires an increased planning effort, since several institutions are involved in constructing a building. For example, there's the building owner, the building maintenance, the building planner, and of course then the construction company. So what is actually required is a flexible automatic production. And here in the image on the right side, I show a little bit like an example. If you have the handcrafted BIPV modules, which have a high level of customization available, but they're also quite high priced currently. And then on the other end, we have the standard modules, which have a lower price, but also very low level of customization. So what is really required is an industrial produced custom-made BIPV modules. And I would actually also show some technologies which can be used for that, continuing what also Eszter introduced in the previous presentation. Next, I would quickly talk about device integrated photovoltaics, since here in this case, it's also very interesting and already explored market. Here is really the option to have solar as a power resource from oftentimes self-sufficient devices. The solar yield is actually not the main requirement, but mainly the functionality and usability of the device. Usually there are lower number of margins, especially when talking about watt scale and PV power. However, higher margins are actually possible to achieve. And here again, the production of a whole system is required. So thinking about the photovoltaics, the power electronics, and also the design of the device. And last but not least, also high quality is required. High quality, not mainly in terms of long-term stability, but in terms of touch and feel for the customer, since most of these technologies or devices are used in combination from customers who then experience the solar energy by themselves. Lastly, I want to talk about vehicle integrated photovoltaics, and vehicle photovoltaics actually provides an additional user benefit or customer benefit, and therefore I have also a few more slides. The advantages are, of course, we can replace already existing vehicle parts, and we can directly couple the energy demand. So we are actually using the energy where it is produced. And this may also, in vehicle integrated photovoltaics, may also increase the comfort for customers. So here on the right, I have a diagram. I have a diagram which shows the consumption of the vehicle depending on the roof area, and the consumption of the vehicle and the roof area of the vehicle. And here, as a color code, we see the potential solar range for a vehicle with the respective roof area and consumption parked in Freiburg, Germany, without receiving any shading. And what we see here, that for currently available electric vehicles like Nissan Leaf or the Tesla Model 3, that actually 1,900 until up to 3,400 kilometers are actually possible to achieve on those currently available electric vehicles. So the customer benefit is actually an increased range with solar energy, reduced charging stops, and historically it was also discussed to have a cooling available for the vehicle. Of course, we have increased requirements for the module design and increased safety requirements for the module. And another disadvantage or challenge is the optimization of the energy utilization, since you, when you have the energy available, you also want to use it. And So far, I've talked about the roof area of the vehicle, but there are also many other parts of the vehicle available where we can install solar energy. So here we would like to suggest a metric or categorization for the vehicle body parts. So on the first level, we have the roof area. Here, this module technology is quite similar to currently available module technology. We add some curvature, but it basically can be used like a standard glass module with curvature. On the second level, we have the front hood and trunk. Here we have a sharp increase in especially in safety requirements. The module itself needs to be some sort of shock absorbing, but still we have a high yield possible for this level. On the third level, we consider all non-transparent surface of the vehicle, especially the sides of the vehicle. Here we have some further requirements regarding safety, but also scratch resistant. And we have potentially a lower yield of this monitor, of this surface area. And last but not least, the fourth level would be even the transparent car windows or the car parts, the windows. And here we can use transparent module technology, which is also available. So now, how much range can we actually generate with these different areas available on the vehicle? So I've already mentioned that with the roof area and an average consumption, we could generate roughly 2,000 kilometers per year for car parked in Freiburg, Germany. On the second level, we increase the area by another 3 square meters, and we can generate even up to roughly 5,000 kilometers per year. Considering the third area with the lower yield, we arrive at roughly 6,500 kilometers. And even adding the transparent car windows with the lower efficiency, we arrive at roughly 7,000 kilometers as a potential driving distance. And 7,000 kilometers basically roughly translates into that there's virtually no charging required during the summer in Freiburg. So now this is current technology. We actually move forward, we develop further. So 20 kilowatt hours per 100 kilometer is a quite average consumption already today. So using a lower consumption, which is actually possible currently as well, with 14 kilowatt hours per 100 kilometer, we can actually arrive at roughly 10,000 kilometers as a solar range per year. And then, of course, solar technology moves forward. We see tandem technologies in development. And with this new solar cell technologies like 3.5 on silicon and perovskite on silicon, we can actually achieve 15,000 kilometers as a solar range for a vehicle parked in Freiburg, Germany in the sun. And this is actually the average vehicle driving distance of an average German car. And this basically means that calculatively, theoretically, we can cover the driving needs with solar installed on the vehicle, which is a much more interesting user benefit and actually also allows higher costs of a module. So now that I introduced the different technologies itself, I want to talk about the technical potential of those different technologies and concepts. Of course, for agriculture and building integrated photovoltaics, we have the highest technical potential available because of the large areas. Then for road integrated photovoltaics or vehicle integrated photovoltaics, we also have a significant technical potential in gigawatt scale. And this is by far different from a niche market potentially. So here we really see that we should actually move forward and go beyond a niche market. Those altogether, the technical potential adds up to 3,400 gigawatt of all these integration applications I introduced. And this is even much more than required for our CO2 targets in Germany. So now I have talked about the technical potential and the different integration concepts. Now I would like to talk a little bit about the technologies. So first of all, we have, of course, the module technologies, but also there are the system technologies. As the module technologies, I would talk a little bit about the multi-junction solar cells, since they are really adding a great benefit to integrated photovoltaics. Then I will also talk about the high and efficient premium aesthetic modules, which is actually driven by the interconnection technology, also as Eszter previously mentioned. Then I will talk about a little bit about colored modules and the module materials and 3D curvature. I will not talk about the system technologies today, since my expertise in the module technology, but it's still very important. So for system technologies, we have the mounting system, which is really required and needs to be talked about an integral part, as well as the converters or maximum power point trackers, as well as battery or the controlling system of the devices. And of course, there are the planning tools, which really is a high requirement, since without any planning, or without an automated planning, it really becomes difficult to achieve a large utilization of integrated photovoltaics. And then last but not least, there's an app programming. I also included that because it's really also important that the customer, the end user, has a direct connection to how much electricity and he saves, or how much money he saves. So, but let's look about into the module technologies. So basically crystalline silicon we have considered in this technology, and it has been shown that it has made quite stable advances during the last years. So we have the aluminium BSF solar cell technology, which arrives at roughly 20% efficiency average. Then we have the PERC technology, recently rolled out into the market, arriving at 23.5% efficiency. Then improving and moving forward, there are passivating contact technologies, and then even passivating the contacts in combination with back contacted and back junction solar cells, providing the highest efficiency. However, there's a limit for crystalline silicon, the OGL limit, and 29.4%, and we are really approaching that limit. So what comes after we need to have multi-junction or tandem cell concepts. With multi-junction or tandem cell concepts, it can really improve the utilization of the solar radiation, and we can achieve higher efficiencies. So basically what it means, more absorbers, more junctions, higher efficiency. But I also want to say, or want to mention, that concentration of the light may also lead to higher efficiencies, or can also lead to higher efficiencies. So here on the slide, I would briefly mention the two main technologies currently explored as a tandem solar cell concepts. Of course, there's the 3.5 solar cell concepts used in space applications throughout the years, and offering the highest efficiencies throughout the last decades. Then there's, of course, the quite recently coming up, the perovskite solar cell technology, which has also very recently explored in combination with silicon bottom cells. So perovskite in combination with silicon solar cells. So, but what are the challenges of those tandem cell concepts? Of course, the cell cost. This is really the main driving factor, especially for 3.5 solar cells. They have been previously, well, they are usually manufactured on germanium wafers, and those combination has almost 2 orders of magnitudes higher cost than crystalline silicon solar cells. Using silicon solar cell as a bottom part instead of germanium, we can actually reduce the cost significantly, but there are also cell production equipments and new cell production technologies which can even lower the cost significantly and may be able to reach a range closer to crystalline silicon solar cells. Then, of course, just to mention that there's also concentrating PV, where the cell costs are in the same range as crystalline silicon, but however, the module costs are, of course, higher because of the concentration which is required. For the perovskite silicon technologies, the costs are actually not the main driving factor. Perovskite silicon solar cells are actually in a reasonable cost range than crystalline silicon solar cells. However, here the technology is still quite new, and it still needs to prove that it's able to show all the long-term stability requirements which are necessary, especially for integrated photovoltaics. So sometimes I always hear, those tandem solar cell concepts, that is really something which is far from being applied currently, and it's something which we should be concerned with in like maybe 10 or 15 years, but that's actually not true. We really see that it's currently really starting up, and probably in the next 3 to 5 years, or even within 2 to 3 years, we will see an increase in tandem solar cell concept coming up. So examples, the 3.5 tandem solar cell concept has been explored, is a mass market on a very large, small scale, but it is a mass market for space applications. Then for the perovskite silicon solar cell concept, Oxford PV is actually ramping up a production facility with 125 megawatts in Brandenburg, Germany. And they also have a quite nice and strong partner with Meyer Burger. So this is really the tandem solar cell concept technologies is really a technology coming up and being relevant in the next 3 to 5 years. Then talking about the next technologies, the interconnection technology for integrated photovoltaics. Here I would like to introduce the shingled interconnection technology, which we are also developing at Fraunhofer ISE. So for the shingled interconnection technology, the solar cells, the previous solar cell is overlapped by the next solar cell, and the top part of the previous solar cell connects the bottom part of the next solar cell, and therefore the solar cells are connected in series. And with this technology, it's actually possible to maximize the module area, maximize the active module area, and maximize the module efficiency. Here we usually also use smaller cells, and therefore we can increase the voltage level for module, which has other advantages for integrated photovoltaics. We also developed the matrix interconnection of those cells here in the right image, where the cells are displaced, well, where the next row of the cells are displaced by half a cell. Therefore, we have a really connected matrix of solar cells, and which improves the shading tolerance or the shading technologies of the module. This matrix interconnection also provides a very homogeneous optical appearance, and currently high throughput manufacturing tools developed by M10 Technologies for this matrix interconnection. On the next slide, I would actually talk a little bit and compare the different interconnection technologies in terms for integrated photovoltaics. Here we have the IBC full cells, which are also, of course, often explored for building integrated photovoltaics. We have the half cell technology based on PERC solar cells, the shingled solar cell technology based on PERC solar cells, then multi-busbar technology for PERC solar cell. Multi-busbar means a round wire interconnection on PERC solar cells, and then there's the smart wire interconnection with heterojunction solar cells from Meyer Burger, which also uses round wire but with a special technology. Looking at the power, of course, IBC full cells and the smart wire technology offer the highest power output of all these interconnection technologies. Looking at the costs, the half cell PERC cell is the lowest, offering the lowest cost, the cheapest option available. But looking at the design, the shingled cells actually offer intrinsically already a very nice and homogeneous dark appearance, which is not met by the other technologies. Even for the IBC solar cell technologies, one needs to adjust the backsheet area and the interconnection of the cells such that there's no interconnection visible. From the voltage level, it's more freely adjusted if you have smaller cells. Therefore, shingled technology also offers here an advantage. Manufacturability is, of course, highest for half cells PERC, because this is really the industrial market right now, and utility scale market. And regarding market availability, the half cells are actually mostly available, but the IBC solar cells and the heterojunction solar cells actually have a lower market availability right now, because there are smaller number of manufacturers for IBC solar cells and heterojunction solar cells. The next technology I would talk about is the colorization of modules and the different module design methods. So of course, there are options like screen printing, where you can make patterns in front of dark area solar cells. We can also make different colors of screen printing, shown here below as an example. Then there are different colored foils available, which can be used in combination with solar cells. Here we have used different colored encapsulants. Then there are meshes and colored nets, which can be integrated into a module and provide also very nice and homogeneous appearance. And then there's the morphocolor technology, which we developed and patented at Fraunhofer. It is based on the morpho butterfly, and it offers a very nice and homogeneous colored appearance while only having very low efficiency losses. Usually those colored module technologies are always a bit more costly and complex. They also require a perfect module design behind the color, like a black module. Therefore, there are also other module technologies available, which have been explored also previously. There's, of course, the black module design, which is a basic requirement for all colored module options. Then this black module design can also be achieved quite easily with a shingled module. Then there's the option of using smaller cells. Here we have arranged the smaller cells with a conductive backsheet such that patterns can actually be formed with this concept. We call it the mosaic module. And then, of course, historically also mostly used are smaller types of solar cells with transparent areas between them to also have some nice visual appearance. Lastly, I would also talk about the module encapsulation technologies and also for the 3D curvature. So first of all, to achieve 3D curvature, there's 3D lamination possible, which is actually required for vehicle integrated photovoltaics. And however, an adequate lamination tool is required to achieve 3D lamination. Then there's the option to manufacture lightweight modules, which are then, after manufacturing, bended into the shape. There are many possible applications for those kind of lightweight modules, also using the lightweight modules even without any bending. However, the long-term stability with those module technology to achieve long-term stability is not very easy. Lastly, I also want to quickly talk about another concept for module encapsulation, which is very interesting for building integration, which is the TPH technology, which is also developed at Fraunhofer. Here in this technology, the solar cell matrix is laid up onto a glass layer, and then the front glass is just pressed onto the layup, and a sealant is covering the edge of the module. Here we see an image of this technology. This technology has a very high long module lifetime because there's no organic or polymeric foil within the module, which usually is the factor which degrades fastest. However, of course, there are some efficiency losses because the optical coupling between the glass and the solar cell is not ideal. So with that, I would like to conclude my presentation. I've talked a little bit about the technologies which are currently already available for manufacturing aesthetic and high efficient modules. We have high efficient solar cells becoming available. We have new aesthetics interconnection technologies, and colorization and curvature is actually already possible. We have a large technical potential for integrated PV. Even in Germany, only 3,400 gigawatt as a really technical potential. And I've also introduced that integrated PV may even offer for a lower levelized cost of electricity, considering all effects, especially also replacement of other parts, integration into already acquired structure, added customer benefit. The requirements for that is really flexible and automatic production. And an overarching system design. So not only thinking about the module and design, but also about the system and the structure, and in combination of all of that. And therefore, I think we can really achieve and move beyond the current niche market for integrated photovoltaics. Thank you for your attention.
So thank you very much, Martin, for that journey through the integrated photovoltaic. It was really very nice, and I didn't stop it because it was so large view about the integrated photovoltaic, of course, which is a really very interesting applications as you showed to us. And one of the things that really I found very, very pity, that all the manufacturer, I would say, they don't really look into the small things. For instance, I do have here in my hand what I call it my portable solar panel. It has a connection and they have many plugs, and I can plug it to my iPhone, I can plug it to my BlackBerry, no BlackBerry, I'm BlackBerry man, to my BlackBerry, to my laptop, to many things wherever I am. It's very slim, it's very small, and it's very light. So and I think that market is only huge. If we consider, for instance, the billion inhabitants in Africa, for instance, and what markets represent for them to have such things, and maybe somehow little more powerful. For instance, the example that you showed for the urban photovoltaic, this also a very good applications, and we did with my company, for instance, the solar street lights with the Wi-Fi and with USB plug to charge. It's very, very interesting application. For instance, the more and more we see, for instance, in the during the summer, everyone is outside under the sun and they use umbrella with a lot of byproducts. I would say they are not neglected. We can find them in the market, but they are still very, very marginal, very marginal. And by multiplying this kind of byproduct, also it makes solar much more known. And I don't know, of course, that the cost of this is not in comparison with a power plant or even a rooftop, which is a really pity. The agri-photovoltaic, it's also something which is extremely, extremely interesting, and they saw that in many places around the globe, and how we can combine the agriculture and the solar, and it's beneficial for the land and for the animals. I saw that. I saw the animals, how they behaved, and all the agriculture and I spoke with, they told me that the animals have another behavior, better behavior. So one of the points that I noticed, and also it's one of the questions that comes regarding, for instance, the roads. I know that one project has been done some years ago in France. I don't hear much other projects since that one. And I know that in China, they developed also some roads, but we never really heard about the performance, about the durability, about all these kind of things. What do you think about that? It has a real future. It's an application by itself, of course, that we can have outside. Rather than thinking about the construction of the road, we can integrate a solar panel that has special design, and it's done. But it is realistic to think about that.
Yeah, definitely. So the last week at the EOPVSec conference, we actually heard from CAINES that they are currently developing the second technology for the road integration together with Colas and Wattway. So I'm really looking forward to this technology. Additionally, there's the German company Solmove currently looking into this technology and really making first steps with first installations. So I'm really thinking that road integration is definitely an option, and we should look into that into the future and develop that further. But there's of course also the solar roofing, so putting roofs made out of solar onto roads, which is also a project which we are currently working on. In this case, you also have the benefit of covering the road with solar modules and protecting the road itself from the environment, and reducing the degradation of the road from traffic and from the environment. So there are several options to actually use roads and the road area in combination with photovoltaics. And I'm really looking forward, and I'm very curious which technology in the end will then succeed.
Okay, so somebody tell me that the project in France is still alive. Good to hear that, but I don't know about the performance. We would like really to know more about that. Regarding, yes, for the road, for the road, I would say surfaces that we have. I saw, for instance, just not far from my house here in Switzerland, the highway at the entrance of the highway, there is, I would say, a huge panel of over maybe 2 kilometers of the glass to protect, because there are buildings just aside of the highway. So to protect them from the noise, and they build, but it's just made the glass, and it's a pity. And of course, this is a really, and I always ask myself that this is really a good application, because it doesn't bother anybody. It maybe shows somehow a nice landscape, and also it's beneficial. It's beneficial for sure. For sure, I can see. I see. Regarding the applications also that you mentioned, and the technology for the car. Here, there's one question that says are the colored modules for the cars in the futures? How important are they?
Yeah, that's a very good question. So I think currently looking at cars and vehicles, the coloring is actually not maybe the most important part, but for the first customers who are interested in a solar roof, they actually want to show their technology and demonstrate it, and yeah, show their neighbor that the new feature of their car equipped with solar. So I think in the first part, it just needs to look nice. It needs to look very premium quality, but the color is actually not necessary for this vehicle integration at first. But I think later on, people actually also still want to have a different car than their neighbor, so that the color technology is then necessary.
Continuing about the cars, this question comes from me. That you consider the side glasses, but you didn't consider the front and the back. Is it security problem or what?
It can also be considered. I just excluded it because sometimes people were really afraid of this technology, and that you cannot see through glasses through the front glass anymore. But to be honest, we actually don't know how cars may look in the future. We see self-driving coming up. We see that car sharing coming up. So maybe you just order a car to your front door to drive from A to B to your next destination. And then this car may be equipped fully with solar energy outside, and you sit inside. You can see through it. You can see the outside through organic photovoltaics or transparent photovoltaics, and the rest of it is equipped with solar technology, and you're not really care too much how the car actually looks like, and it can be really generate a lot of electricity, and so save the electricity.
Yes, absolutely. The organic photovoltaic is a very nice solution, because you also can have varies your color. And you know, the EPFL, they have here in their premise a building done with this these modules are glass made, and it's very nice, and they have different color. I would say that they have maybe 5 different colors, and you can see through perfectly without any problem. For the technologies, that's fun. Technologies for tomorrow, because you show that to us different technologies, and especially when we go into the, I would say, the junction, double, triple, and so on. Do you have any, as an institute, of course, do you see a kind of target time frame for the development of, because the double junction, we have been starting from the thin film, double and triple junction, amorphous silicon, and all these things. That's during the 2010, 2012, everybody was talking about these technologies. After 2013, 14, doesn't exist anymore. And it was very promising in that time, the double junction and triple junction. They reached over, I guess, if my memory, 15% efficiency in that time for thin film, for the amorphous, microamorphous indeed. Microamorphous. Do you see any, I would say, move on that?
Yeah. So looking at the two different concepts which I introduced, the 3.5 solar cell technology on silicon, this is really a cost factor. The technology is available currently. If you want, you can actually manufacture modules with this technology, and they are long-term stable. Both technologies have been proven in the market and in applications. So in this case, it's really a cost factor. And if you can extend, if you don't have any charging needs anymore from a vehicle, this cost factor may even be possible with this technology or to achieve for this application. Then looking at the perovskite on silicon technology, this is of course a more new developed technology. However, I'm confident that already this year we will see large modules available, or large modules not available but shown and demonstrated by different companies with perovskite on silicon. So I'm confident that we already see that this year. Still, it needs to be proven the long-term stability of this technology. However, it's more a module technology factor here, because we need a sealing, a tight sealing. We don't want to have any water coming inside into the module, and this is actually quite well researched already how to achieve that. So I don't see any principal barriers for the perovskite silicon technology to be applied in the market.
Okay, Martin, so with that, we're gonna conclude, and thank you so much again for that large journey across the integrated photovoltaic. And unfortunately, I have to announce that Mr. Larsen Bach from Avansis, he cannot be with us for personal reason. So I apologize on his behalf. And we're gonna move to our next speaker, who is Mr. Jean-Luc Kwantes from AKUO Energy. Jean-Luc, the floor is yours, please.
Thank you, Nabih, for the introduction. So, first of all, a few words to present myself and AKUO. AKUO is an energy producer, a French energy producer, which is independent, existing since roughly 10 years. And decided, I would say 4 years ago, to start a new activity, which I'm trying to lead. This activity is the industrial part of AKUO. In this industrial part, I would like to share with you a point that we mentioned already, and what I call here from manufacturing to time to market. Time to market for the sun-style PV tiles and the floating PV, but let's focus on the sun-style PV tiles. What I want to raise here on the manufacturing to the lead time is the time for certification, what we raised, and the time that has been needed to develop and certify the tiles as a product for construction and recognize as a product for construction, which is really a long journey to be able to put this product on the market as a PV tiles used by the roofer as a, I would say, normal product. So this is what I would like to share with you in this small presentation. So if we go to the next slide, here is from beginning of 2019, our product target roadmap. This was written in 2018, what we will put on the market. So it was more than 2 years to be able to have what we call in blue, in dark blue, sun-style original 24. So before that, we have to go through a BIPV on the wooden structure for the roof, then a BIPV on the steel charpente, and of course you need to get the ATEC and to go on the green list to be able to sell this product. So, and then you start to introduce what has been presented before, the new sales, you listen to the market, you listen to the architects, you listen to the constraint that you get from everybody, from everywhere, and you have to develop your product and you have to make it more competitive, etc. So you see, to have the second, I would say, family of SunStyle Evo, it's more than 3 years to be able to recertify everything, to recertify from an IC perspective, and to recertify as a construction material. So this lead time is really, really very important. So that means that we need to introduce from the early beginning, when you start to work on the roadmap, when you start to work on your product, to see what will be the end, what is the target, to make sure that what you are going to certify is the product that you want on the market. Otherwise, you missed 1 year or 2 very easily. Of course, on the green bottom, we speak about recyclability of all this material and the way to package. The packaging of it is huge. So where we are today, it's we are starting to make our first BIPV roof. We are starting to build, I would say, 30 roof this year, and of course we want to increase drastically these numbers by having by using this certification and by using the manufacturing center that we are using today. So if we go to the next slide, here is the succession. This is the certification process more in detail. So you see the TÜV certification. What was needed, really, the AC certification from the TÜV was, of course, very long also, because this is a long test in terms of reliability, in terms of you know all the tests that we can make, and we need this TÜV certification, this TÜV input. Output was the input for the CSTB, and to take that, to start to take this product as a construction material. So it was from the beginning, when we start to the first drawing, the first samples on the first line, which was end of 2018, we get this certification mid 2020. So it's really a long time to get this certification. Of course, that's mean that you have a line, you have a production line which has been also certified, etc. If it's not the case, so you're in trouble, or you are adding the time to market. And I think more and more, and like you explained in the previous presentation, what's the architects want is something that is corresponding to the market. So we need to anticipate, and we need to make this time to market as quick as possible to answer to the architect needs, to the roofer needs, etc., etc. So there is a real constraint here. If we go to the next slide, it's quite illegible, but this is only the certification process for the French case. So this is more than 18 months if you are adding everything to get everything certified with the commission, the different submission in papers, in samples, etc. It's a real tough job. So just to visualize, if we go to the next slide, here it's the preliminary step before to make this factory or gigafactory according to your business, to make it ready. All these steps are essential, very simple but essential. The first is a business update with the product roadmap as we see, the certification roadmap as we see, the roadmap for France in international market, the key leads, the organization, how you are going to lead the market and how you want to cover the market. The second one is the segmentation, the value creation, and the competitivity, which is another big topic. And then you can think about what is the way to produce it, to make it manufacture, to make sure that you will be able to have the right capacity to manufacture the number of panels, the right number of panels, the right number of tiles, whatever. So you need to go through all these steps before to make it. And if we go to the next slide, it will be, I would say, 4 steps to go to what I call a gigafactory. A gigafactory, this is, I would say, our target. We can be at 300 megawatts, etc., but something huge. The first step is to define the target cost on the P&L for this industrial setup. Everything on paper. You need to write everything very precisely. The lead time, the takt time, the capacity, the overall capacity. Then after that, the next step is up to 150 megawatts. It's to confirm the competitiveness. And if you go to the slide before, thank you, Julie. To confirm the competitiveness. Then the third step is up to 300 megawatts, is to demonstrate in reality the competitiveness and to have the right automation level, which is key, like we have seen in the previous presentation. And then you launch, you have another step to launch a gigafactory or up to 300 megawatts. You duplicate what you have studied in the previous step. Just for some numbers, a gigawatt factory is 20 lines. One line is 50 megawatts. There is a huge investment, 100 million euro. The surface is 20,000 square meter. This is more than 100 trucks per day. And this is around mill collapse around. Of course, we want to make this, and we target to have these manufacturing facilities in Europe and somewhere in this area, which is representing 9 million tiles per year, which is 38,000 tiles per day. So it's a big deal. And to go there, so that is big numbers. So if we go to the next slide, there is some principles and to develop these manufacturing facilities according to the sales, of course, to the real sales volumes. There is a phase 1, 50 megawatts, a phase 2, 100 megawatts, and a 300 megawatts, with roughly the investment level and the time, the lead time that we need to add to that, which need to be added to the previous lead time that we speak about the certification. So if we put all together, you see the time that we need to construct a line, the certification, it's very long, so it needs to be anticipated 2 years and 2.5 years before, I would say. If we go to the next slide, this is a resume. Thank you. In terms of manufacturing, from the starting point, this is 5 months to prepare the production area, 12 months to prepare the equipment, to get the equipment inside, 3 months to validate the equipment. For the product validation, this is 10 months to be certified by a third party, as a tube, for example, and 18 months to be a construction material certified by the CSTB, for example. So anticipation and planification are key between 12 to 18 months to get equipment and certification in due time. Always use the manufacturing facilities in a push system according to the customer demand. So we need to be answering to the customer demand. Otherwise, if you have too much volumes, if you are producing too much, too quickly, it's from a financial standpoint, it's of course non-economics. So this is a key. And this has been to be anticipated, as I said, 2 years and a half before. So this is all the key items to be strongly analyzed. If we go to the next slide, these are some pictures of tests that we have done from the product made in France. So here is a TÜV. If we go to the next one, is another one done in the CSTB, which is a Moby Dick test. So big deal to make all this maquette and test. If we go to the next one, it's another picture to the test for wind resistance and water resistance, and to make this very strong test to validate the different inclination that the roof can have. When we validate here the black tiles, this was working for also the other colors for this kind of test, not in the TÜV, of course, but here it was the case. And the last slide is another test, which is in the CSTB, which is the wind, also the wind resistant, another test to the depression. And the last one is a fire. The last slide is the fire resistance. So you can understand that all these tests are very, very long and takes a lot of time. So this was this presentation for you, from manufacturing to lead time and time to market.
Thank you, Jean-Luc, for your presentation and the overall also journey that you give us through a project from starting point until the end.
Thank you.
It's
Pleasure.
never an easy pathway to start a manufacturing in Europe in general and in France particularly.
Right.
It's extremely complicated, but anyway, I'm very glad and happy for you guys that you really make it. One of the questions that comes to my mind before we go through other questions from the audience, I would like to ask you, please, how can you, I would say, decide to go for 1 gigawatt without creation, without the entire ecosystem? Because 1 gigawatt, as you mentioned it in your presentation, is going to need a daily 100 trucks moving the modules, but maybe even more bringing raw materials and handling all the shipment, handling the inventory. It's not an easy matter. So how did you plan to manage that?
So we were part of the constraint is to have a green factory. Of course, to go to the gigawatt will not be the first step. It will be this factory will be made step by step and by 50 megawatt and 50 megawatt. So step by step, it will be 3, 4, 5 years. I don't know, according to the customer demand. So this factory will be a green factory with trucks working or being moving with the hydrogen. We can use the hydrogen also internally with the logistic in the warehouse for the logistic. We can. Our intention is to have really to use green energy at every step of the full integrated process, not only to make the panels by itself, to make the tiles by itself, but for the incoming goods, for the outgoing goods, to have these trucks, to have these internal hydrogen small vehicles are our intention. Also, we want to make it, as I mentioned, in Europe. So we would like to use cells manufactured in Europe, of course, to have glass made in Europe, to have all these materials, to have a carbon printing as less as it could be. So it's really an objective.
Yeah, well, I think that when you plan, because you mentioned it, that's the planning of the project is a key for the success. Planning in advance, it's absolutely necessary, but also having this kind of, I would say, plan regarding the ecosystem and the supply chain is crucial for the success too, not only for the cost, especially now where the transportation cost is getting more and more, I would say, effective in terms of cost distribution.
Yes, correct. Correct.
Yeah, this is one of the questions here that comes from the audience. How does the certification process compare with other countries?
It's the French certification is one of the, I would say, not, the word is not appropriate, but excuse me for that, but is one of the highest standards. When we have to sell tiles, I would say in Norway or in Dubai, in foreign countries, maybe we have to add a specific test. For example, for Dubai, it was a specific fire test. For Norway, nothing else. So this is when we are French compliant, we can say that we can sell in the most part of the world. Huh? It is one of the most complex, definitely.
Yes, but this is I would say, are you talking about special certification or the standard certification? Because normally the tests for both TÜV standard are the same. We can add other certification, like for salt mist or PID, or I would say even sandstorm, or these kind of things. But what is different to make them, you know, one of the toughest and one of the best?
The particularity in France is you need to get the certification from the CSTB as a construction material to be able to be on the green list. And when you are on the green list, that means that your product can be insured, that the guy, the roof guys can be insured to put these PV materials on the roof for the next decade, because they are obliged in France to have an insurance covering themselves during the next 10 years. So to do that, you need to have this green list, and you need to have this certification from the CSTB, which is, I think, unique in France, to have this insurance for 10 years for the guys to put it. La décennale, assurance décennale.
Yeah, I know. Well, that's for sure that CSTB is typically French.
Yes.
This is for sure. This is for sure. But the things that I never really understood that this how it doesn't apply for the modules coming from outside. And this creates a kind of discrepancies between the modules coming from outside and the modules that we impose to them to have that kind of certification.
I think even the product coming from outside should go through if we want to have the people who are making the roof insured by their insurance company. That is sure.
Yeah, to have the insurance, I agree with you. But if they don't need the insurance, because the insurance is something which is, I don't know how many installations are insured.
It's an obligation. This is clearly an obligation. This is according to the law. And,
this is by law.
This is by law. And for example, we are, as it is now, we are meeting all the head of insurance company to describe our product because they don't know this product. So they are not able to insure it. So we are making a roadshow, I would say, in France to meet the head of this insurance company to describe our product, to describe our certification in the TÜV, in the CSTB. They need to understand what is BIPV. This is a main step for them to insure their guys, which are everywhere in France. And they are insuring them for the next 10 years to put this kind of roof. So this is a new stone, a new stone in their capacity to make this kind of roof. We are changing the roof job.
Okay. One question regarding, I guess that you answered somehow in hidden manner the question, but I want to ask it because it's interesting. What are the characteristics of the sun style? And why this size of cell?
The characteristic of the sun style is the black one is 870 millimeters per 870 millimeters, 87 centimeters, and the black one is 115 watt, and the terracotta and the gray one are 85 watt, same size. The cells, what we are using is a very classic cell, as it is now, and we are developing our roadmap, as I show in the first slide, to change the cells and to be adapted to the new generation of cells, as it was described in the previous presentation, to take that in consideration, of course, and to make sure that we are going to certify our product with a good cell to have the right power, etc., etc. And this need to be done relatively in advance before putting that on the market.
Another question: will you have training program for construction managers and workers?
Yes, we have on the manufacturing site. We have put a training center to train the roofer for this new job. There is a theoretical part. This is a 2 days training, 1 day theoretical and the other day practical, with a real roof at 1 meter from the ground. But they learn, and they learn how to fix, to mount, and to make this full assembly system with the electric device. And this is where we are asking them to have the right certification, BIPV, to touch and to connect, because usually they are putting normal ties, so they are not. They need to have this certification, the BIPV certification, which is another certification. So we go through this training, yes. And we go to this training even before the project, for them to have a know-how for giving a good price, because today, as they don't know the product, they don't they cannot make a price to the final customer. So they need to know this new technology, this new job, this new time, this new constraint or not, for them to make the right price, the right cost.
Okay, okay. You pronounce yourself the word cost. I wanted to avoid it, but as you you pronounce it, I want to ask you about the cost. What percentage, if you compare your modules with the others regarding the cost of, I would say, the full system integrated EPC, for instance?
You say the cost of the furniture and the cost of the man hour. I would say the cost of the roofer.
Yeah, the EPC, for instance, if we say that, for instance, installing modules on the rooftop in France maybe cost about €2, let's say, roughly speaking, what percentage would be or what would be a range of your products if we consider their features, their differentiation, and their need for specific installation?
Okay, so the furniture is the electric photovoltaic, the tiles by itself. The electric photovoltaic system is I would say 40%, and the 60% is the electric device, the micro, all the electric system, and the man hour to put the tiles on place with the micro inverters included. So 60 for the micro inverters and all the electric, the man hours to put that in place with the tiles, and the furniture is 40%, roughly.
Yeah, I understand your numbers. However, if we compare apple to apple, you understand, we go direct. An EPC rooftop maybe costs, roughly speaking, let's say €2. Okay. How much is gonna cost, maybe based on that €2 as a reference number, is gonna cost 120%, is gonna cost maybe 30% more, or is gonna cost 10% or 20% less? So I don't know exactly. I'm just
it's what can I say here? Depending if we're taking a normal roof with no specificity, it's more than 50%. The time to recover the investment is exactly, this is another number that we can compare. The time to recover the investment is between 8 to 10 years.
Okay. So I think there is, I don't know, that was the last question from the audience. So I think with that,
thank you.
We're gonna finish here. I would like to thank all the speakers of today. I think that they give us a real overview, bringing us through all what we can do with the integrated photovoltaic, different applications, and the technology also. We saw through the last presentation from Jean-Luc how important is the planning for the projects also, and how we can go from the manufacturing to the product. I wish you, Jean-Luc, all the success. And I would like to thank all the speakers and the participants to that session. And thank you so much, and hope seeing you soon in our sessions that we are continuously organizing through the year. You will receive all this kind of information. So thank you so much, and I wish you a good day.